The next part of working with complex numbers in polar form is to learn about De Moivre's theorem. Okay, this theorem is just taking the what we know and have just learned about multiplication of complex numbers in polar form just a little bit further. We know that if we were to multiply two complex numbers, we need to multiply the moduli. So if we're raising a complex number to some power n, then clearly the moduli will be raised to that same power. And because we add together our arguments, there will be the number of arguments being added together that are the same will be whatever the power is. Okay, so z to the power of n means there'll be n lots of theta. Okay, and so we go n times theta. So that's just taking that multiplicative property a little bit further. Okay, and we'll use this quite a bit. So let's look at the next example in these. So what we've got here is given, not in polar form but in rectangular form, these three complex numbers, and each of them are being raised to these different powers. So what we're going to do first of all is to consider each of them separately and put them into polar form, and then use De Moivre's theorem then. So if we have a look at our first one, 1 plus I, then our value for r for that, okay, our modulus is found by going 1 squared plus 1 squared, and then taking the square root of that, so it's the square root of 2. Okay, the modulus for the square root of 3 minus I, alright, we square the square root of 3 and add the square of negative 1, and so that gives us 4, so the square root of 4, which is 2, and the modulus for negative 2 plus 2i will be negative 2 squared plus 2 squared, which is 8. Taking the square root of that is 2 root 2 in its most simplest form. And then we need to look at the arguments for each of them. Alright, so remembering that when we do that, we need to consider what quadrant it's in. And the first one here, 1 plus I, is in the first quadrant. And so we know then that we just need to consider arctan of our imaginary part over the real part. So 1 over 1 is 1, so arctan of 1 is going to be pi on 4, so that's our argument for that one. For the next one here, okay, square root of 3 minus I, that is going to be in the fourth quadrant because the real part is positive and the imaginary part is negative. So that's going to be found by considering 0 minus our angle, our basic angle. Remember, our basic angle is just in the first quadrant, but we want to be in the fourth quadrant, so it's 0 minus our basic angle. So that's what we write, 0 minus arctan of 1 over root 3, okay, which is going to be negative pi on 6. Because of arctan of 1 on root 3 is pi on 6, but it's 0 minus pi on 6, which is negative pi on 6. And then thirdly, negative 2 plus 2i, the negative real and positive imaginary means that it's in the second quadrant. And so to get the appropriate argument for that, we go around to pi and then subtract our basic angle. Alright, so it's going around to pi and then minus our basic angle. Alright, so that's what we've written here. Pi minus arctan of 2 over 2, which is 1 over 1. Obviously arctan of 1, which is pi on 4, so it's pi minus pi on 4, which is 3 pi on 4. So that's our argument. So we've got here our modulus for each of them and our argument for each of them as well. And so that's summarised here, just changing those to polar form. And so applying De Moivre's theorem then, we are raising our 1 plus I to the power of 4. So we need to raise our modulus square root of 2 to the power of 4, and we need to multiply our argument by 4. Okay, square root of 2 times 4 to the power of 4 is 4. 4 times pi on 4 is pi. The next complex number, square root of 3 minus I, is raised to the power of 3. And so we raise our modulus 2 to the power of 3, which is 8. And we multiply our argument negative pi on 6 by 3. So that's going to be negative pi on 2. And so that's our complex number raised to the power of 3. And then the last one is our negative 2 plus 2i to the power of 5. So modulus to the 2 root 2 to the power of 5 is going to be to result in 128 root 2, and we multiply our argument 3 pi on 4 by 5, which is 15 pi on 4. Now we want to simplify that. We want to bring it within that that range, you remember, from negative pi to pi. Okay, we want to bring it to within that range here, and obviously 15 pi on 4 is outside of that, so we just simplify that down, work out whereabouts it is, and it's negative pi on 4. And the simplest way to think of that is we've got 15 pi on 4. Well, what's that as, say, a mixed number? Well, 4 into 15 goes 3 times with 3 left over, so that's the same as 3 and 3/4 of pi. Okay, so starting here, we go around 1 pi, 2 pi, 3 pi, plus another 3/4 of pi is going to be here. Okay, which means that's the same as negative pi on 4, and which is why we've got negative pi on 4 here. Okay. Now the next step then is to put those together. So we've got our rectangular form of what we're working out, and then after we've raised each of them in polar form to their respective powers, this is what we have. So now what we do is we multiply the top using our understanding of multiplication of complex numbers in polar form, multiply together the moduli. Okay, 4 times 8 to give 32. Add together our arguments. Okay, pi plus negative pi on 2, which will be pi on 2. And so then we look at our division. Okay, so 32 cis pi on 2 divided by this one here. Divide our modulus up the top and the bottom, and that's going to simplify to 1 over 4 root 2. And then because we're dividing, we're going to subtract our arguments. So pi over 2 minus negative pi over 4, being pi on 2 plus pi on 4, which is 3 pi on 4. Now you'll notice here that our 1 over 4 root 2 has changed into this form. That's obtained by what we call rationalising the denominator. So if we think of what we have here to start with, it's 1 over 4 root 2. To rationalise the denominator, we multiply by root 2 over root 2, which gives us root 2 when we multiply these, and multiplying the denominator is 4 root 2 times root 2. The root 2 times root 2 is 2, so 4 2s are 8. So that's where that comes from. Now you'll notice the question's given in rectangular form, so it's a good idea then to give your answer, unless it's stated that it doesn't matter, put your answer back in rectangular form. And so how we change polar form back to rectangular form is that we need to write out in full, okay, our polar form. So root 2 over 8 cis 3 pi on 4 in full is root 2 over 8 times cos 3 pi on 4 plus I sine 3 pi on 4. And then we work out our cosine and sine of each of these values for theta. Cos of 3 pi on 4 is negative root 2 over 2. sine of 3 pi on 4 is root 2 over 2, and then multiplying throughout when we expand. Okay, root 2 over 8 times negative root 2 over 2, we're going to get 2 over 16, which is 1 over 8, and so we have negative 1 over 8 for our real part, and our imaginary part, root 2 times root 2 is 2, over 8 times 2 is 16, so it's positive 1 over 8 I. Okay, so that's our answer in rectangular form. So as you can see from what's written in your notes, okay, having watched these videos, you can now work through exercise 3E in your textbook, okay, and specifically these ones I've specified. Very afraid to do more though, you can go and do others. And from the Steve Watson problems, 44, 45 and 47 to 54. Okay.